Okay, perfect. Thank you so much. So, welcome everybody to this first PhD talk of the new series of the new semester. So, thank you all for being here. Now, let me just spend a few minutes on some more technical, let's say, details. As you know, starting from this cycle, we will have also a prize associated with the PhD talks. So all the seminars will be evaluated by a committee and by a popular jury. The committee is composed of 4 members, the 2 PhD representatives in the department council, and 2 members who are delegated by the coordinators of the 2 PhD programs. So for this semester, the 2 members are Professor Cornelli, delegated from the PhD program of ISSG, and Professor Bocchiola from IAI, I think. I mean, it sounds strange in English. Okay. But to nominate the popular jury, we also need to keep trace, starting this semester, of the people attending each seminar. So I will kindly ask you to fill this table that I will give you in a few minutes with your name and your email. Okay? So now let me just introduce our speaker for today, who is Marco Davolio. Marco is a PhD candidate from the 38th cycle, if I remember correctly, and his research is focused on finding strategies to reduce the yes, thank you. So, to reduce the environmental impact of the concrete industry. So his talk today will be about the evolution of mechanical properties of ultra-high performance concrete affected by autogenous healing under sustained loadings and aggressive exposure conditions. So now, without further ado, I just leave the floor to Marco. I will share the presentation and leave the floor to Marco. So, no, not working properly. So now this should work. Okay. So the floor is yours. Thank you.
Okay. Thanks, Chiara, for the kind introduction, and welcome everyone to my PhD talk. The title was just suggested by Chiara. It's about methodology to assess the evolution of the mechanical performance of UHPC over time, with some specific conditions. We will get into details during the presentation. I will start with a brief introduction to give a framework to the...
So we have to communicate the evaluation criteria for the jury.
Okay, perfect.
Sorry, I was reading the...
Yeah, it's...
sorry.
So it's... you have it there?
Yes, I have it.
I have it here.
Okay, well, it's based on...
So, you have to evaluate originality of the contribution and communication efficacy. And it's 10 points, up to 10 points for the content, originality, and up to 10 points for the communication efficacy.
Okay. Okay, so, sorry, I go ahead. I was saying this is the outline of the presentation. We will start with some introduction to give a frame to the work we did with my research group, and some discussion of the material, either UHPC or UHDC. We will get into details for this, and then present the methodology we developed and the results we obtained. So, I guess this. Okay, should be working now. Okay. As an introduction, I started from one of the most trending topics nowadays, which is the global climate change, which is affecting our global warming. And as we know, one of the main issues related to this are the fossil fuels, which are highly contributing to the emission of CO2 to the atmosphere. And one of the solutions we are developing more and more is the introduction of renewable energies, which are very promising from an energetical point of view. That we know they have some drawbacks, but in general, this is the way we are leading to. There is a problem associated with renewable energy production, which is that many plants have to face very harsh conditions during their service life, that, as we know as engineers, they are designed for a very long service life, and also, since they are very particular structures, they have high mechanical demand and also durability, especially for the ones exposed in harsh environments, such as chlorides, sulfates, or others. As you can see, we have some examples here. And for these applications, we already know that ordinary reinforced concrete is not suitable due to its poor durability properties. For this reason, in the framework of a European project, we tried to develop a new material which counterbalances the lacks of performances related to ordinary concrete. And the purpose of applying this material is to develop different design for strategic structures in different conditions, such as land, onshore, and offshore, which have different exposure and environmental conditions they have to face throughout their service life. And as I introduced the concept of this new material, ultra-high durability concrete, I will now briefly describe its own properties. Starting from the mixed design, the things I want to point out for this are the significantly low water-to-binder ratio, which of course guarantees to obtain a high compressive strength, and also we have delayed hydration, which characterizes this material due to the unhydrated cement particles inside the matrix after casting. Then we have 1.5% by volume of steel fibers, which can give to this material a remarkable tensile strength. So we will see what are the results of this kind of mixed design. Then we have some other components, and the one I want to highlight is this crystalline admixture, which was specifically developed to enhance the healing capacity of the material. So, as I mentioned, one of the main features of UHPC is this mechanical performance, both in terms of compressive and tensile strength, which allows us to reshape our concept for structural design, reducing the sections of the elements, and in some cases, reducing or removing the reinforcement in terms of reinforcement parts, of course. And from the durability point of view, you can see here, this is a real-life application, and the self-healing of the material, the self-healing capacity, closes the cracks that happen in concrete, as we know, and thus fosters the durability of the structure itself, limiting the penetration of aggressive agents inside the matrix, and thus the corrosion of the reinforcement. But all these features need to be implemented in our design process. And to do this, as we know, we need a constitutive behavior of the material. Specifically for UHPC, one of the most important things is its behavior over time, because as we mentioned, we develop this for durability, and durability is a property we need to address over time. And currently, the most diffused standards are this prescriptive approach, where durability is addressed by some requirements we need to fulfill to complete our durability design. But for this material, this type of approach is not suitable because it does not have static, constant properties, but it has a kind of evolving response over time. So the reason why we needed to develop this methodology and to carry on this work was to try to understand how these properties develop over time in terms of constitutive behavior and durability response. So, as I said, we developed this methodology. And here I reported the main characteristic of the methodology we proposed, which was meant to represent as more detailed as possible the conditions a structure has to face throughout its service life. Namely, a long-term exposure, which can be facing different type of environments. I already mentioned chlorides, sulfates. These are two very common applications for offshore structures, for example, or geothermal plants, which you will see later. Then here we have flexural loading, and in general, a structure we know has to face any type of mechanical loading. We study the flexural loading, which has to be applied throughout all the investigated time, of course. And then these two parameters affecting the performance of the material are counterbalanced by the self-healing, which should be able to counteract the degradation of the material and provide constant or enhanced performance over time. And other characteristics of the methodology we will find out throughout the description of it are the repeatability, adaptability, and it involves many different parameters so that we can address different properties of the material. And this methodology was not only proposed, but also developed on a case study where we both addressed 3 different batches of UHPC, which the reference one had only the crystalline admixture in addition to the mixed design I already described for the autogenous healing. While the other 2 batches, having also the crystalline admixture, also had, in one case, alumina nanofibers, and in the other case, cellulose nanocrystals. And we will later find out the contribution of these nanocomponents to the performance of the material. On the other side, we investigated 3 different exposures. The first one is tap water used just as a reference, but what we know is that our structure, for example, in this case, we have a geothermal plant, is exposed to sulfates, and this is a raft for mussel farming, and this is exposed to chlorides inside seawater. So we studied these 2 exposures. I want to mention that for geothermal water, we ship the real water from a geothermal plant to the laboratory to have it for our exposure. And this is the layout of the methodology. I know it's a quite full slide, but we can separate. On the left side, we see all the specimens we tested. For each material, we had 72 thin beams. We will see a picture of them later. The idea was to expose all of them in the 3 different exposures and test them at different times. For the first 3 months, the testing was carried on 9 couples globally, and then we took wider time spans of 3 months up to 6, 9, and 12 months, and a higher amount of specimens. So this is what we tested, and what we did is summarizing these experimental steps, which started on the side of the geothermal plant you saw in some pictures, with the casting of the slabs, which was also helpful to actually see the real condition of casting we face for precast structures on site. And for these slabs, a magnetic survey was performed, and then they were cut into the thin beams we used for our laboratory testing, which started from this first stage, where the specimens are uncracked, are safe as they were produced, and we did these 2 different non-destructive tests that we then repeated afterwards, as you can see from the picture, at stage 2 and 3. Stage 2 is when, after the non-destructive measures, we pre-crack our specimen to induce the damage that the material has to face during its service life. And then, after damaging the specimen, we repeated the non-destructive measurements, and then we applied this frame, this steel frame for sustained load, and we analyzed the cracks on the specimens. After doing this, we put them inside the exposures I mentioned, and after the prescribed time, we took them out. We repeated the non-destructive measurements, namely the crack width and the two I already discussed about, and then we performed the failure test. As you can see here, I talk about couples which are nominally identical, because the idea is that for each of them, one specimen was tested under 4-point bending and the other one under direct tensile test. So now we will go through the steps I briefly described. This is the magnetic survey, and the purpose of doing this was to try to determine the distribution of the fiber, because of course when we cast fiber reinforced concrete, we don't know the actual result of the casting, especially when we discuss about on-site casting, which has some logistical issues. And for this purpose, we used this magnetic probe, which is able to measure the inductance of the material on a thin layer, which was perfectly suitable for our case, since we had nominally 30mm slabs. And from this, we could draw these contour maps. You can see an example here, to see if there was any significant variation of the fiber content inside any slab. And what we observed is that the distribution of the fibers is quite constant on the surface. And I want to point out, I'm talking about the surface and not about the section. We will see about this later. And for this reason, we can consider all the beams we cut from the slabs as nominally identical in terms of reinforcement, which is very important to address their mechanical performance. These are the two non-destructive tests that we repeated 3 times. We have the ultrasonic pulse velocity and the natural frequency of vibration. I will not spend much time describing these tests. We did with the 2 different layouts, each of them. And the purpose is to obtain a dynamic elastic modulus, which represents the condition of the specimen at the investigated time. And we could also relate each measurement with the previous ones to see how it evolved. Here, I present the induced damage, which, as I mentioned, was pre-cracking, and we targeted these 200 microns crack opening displacement. The idea was to obtain a crack width which would be observed from the microscope. We did some trials before finding an accurate crack opening, because literature has some scattering of approaches from 50 to 300 or even more microns. And we pre-cracked the specimen with a 4-point bending scheme, because the idea was then to reproduce the loading condition, which with this steel frame, you can see in this picture, that aimed at keeping the load, 4-point bending loading, constant over time during the exposure. So this frame was exposed together with the specimen, as you can see from here. And the load was applied first on these load cells positioned on the top of the specimen with these steel bars, was then transferred from the load cells to the specimens, tightening some nuts we positioned here below the red ones and above the green ones. And in doing this, the load was transferred and the load cells could be released and moved to the following specimen. The idea of this was to reproduce the pre-cracking condition, but as we know, after pre-cracking with the machine, we had to unload the specimen before reapplying the load. So we verified that reloading it at a specific targeted crack width, better, at a specific load, which was the same we achieved during pre-cracking, obtained the same crack width we wanted to have. And for this, we calibrated the system and we observed it was as we expected. So the condition we see here is the same as pre-cracking. Then we measured the crack width of the specimen by means of a digital microscope. We did both a detailed scanning of just 2 cracks from each specimen, as you can see from the scheme, and in some cases we counted the number of cracks because we expect a multiple cracking regime from the UHPC. This is the processing we did for the cracks. We could recompose the profile of the crack with the pictures we took from the microscope, and from that we binarized the crack to obtain the area. We tried 2 different methods. The first method was manual, which was very time-consuming, and for this we moved to a more automatic method, which was this deep crack code, which allowed us to just give the raw image to the software and obtain the profile of the picture of the crack. We also calibrated this method, observing how much was the difference between the manual processing and the automatical processing. And the difference was below 5%, so we accepted as reliable the automatic one. And the ones I already described are the non-destructive measurements. Then we move to the destructive parts. As I said, the specimens were pre-cracked and then, after exposure, were tested under failure. For the ones that were tested under 4-point bending, we have this curve, which is the pre-cracking, and the subsequent curve, which is the failure. And from this, we could calculate the index of stiffness recovery, which is defined here. Because, as you can see, this is one case without healing, and the stiffness has not significant variation between the initial loading and the second loading, while when the initial loading is at the beginning and then we have healing, we have a slight or remarkable increase of the stiffness. For the failure test, we have a twofold approach. As I already mentioned, one of the 2 specimens from the couple was tested under 4-point bending, and the other one under direct tensile test. The last step of the methodology was to develop a method to obtain a constitutive behavior, because this is what I mentioned as our goal for the work. The problem is that for flexural tests, we only have a structural response for the specimen. And for this reason, we took a simplified inverse analysis method from literature, and we adapted it to our case with the purpose of obtaining from our 4-point bending test a constitutive response. We derived these numerical correlations between the test and the constitutive law. And as you can see, we also controlled the calibration of the method, which was quite satisfying, and for this reason, we applied it. Then I will briefly discuss the results of our methodology, starting from the self-healing capacity of our UHPC, which, as you can see, it developed a multiple cracking regime with many cracks of a very small size, small width, and this fostered, of course, the self-healing capacity of the material, which is able to seal these small cracks, as you can see from the picture. Most of them are sealed. And this is what we experienced here, when after 9 and 12 months, all the cracks were completely closed. And also, after very short periods, we already are between 85 and 95% of crack sealing. And also, the cracks we formed at pre-cracking and that were sealed, they remained closed even during the failure test, which localized the failure on new cracks, meaning that the products developed during the sealing process were effective to bridge and to close the cracks, also resisting from a mechanical point of view. The stiffness was addressed both from the dynamic modulus, or recovery of the dynamic modulus compared to the initial condition and the damage we applied to the specimen, and this confirmed what we observed from the crack sealing. As you can see, in most cases, after 1 month, we are already close to 100% of recovery, and the performance stays still until 12 months, where we observed some slight reduction of the values. And also, with the index of stiffness recovery, which is then a mechanical measure, we observed the recovery up to from 80 to 100%, even after 1 month. And it progressed constantly at 100% for all the periods. From a mechanical point of view, we see some scattering of the results, which is even more significant than the evolution or any possible trend over the time. This means that the specimens are not really affected by the condition they are facing, and they are, on the contrary, effectively healing and keeping their constant performance over time. So this is another confirm of what we was trying to observe. And as you can see from the average curves, from the flexural test and from the tensile test, they are pretty similar, and they are all close to each other and inside of this envelope of the tests. And these are some pictures of the failure we observed. And we will further discuss about tensile failure later. Then, these are the results from the last step I mentioned. I am just presenting two cases, which are the specimens immersed in chlorides and in geothermal water, because what we observed from crack sealing is that for the chlorides, we had this phenomenon of remarkable sealing of the cracks at very short times, which is confirmed by the inverse analysis with this increase of the toughness of the material, while geothermal water performed almost constant over time with some scattering from the first period to the last one. And this is where we experience some reduction of the response of the material. The observed conditions of the specimen after the exposure, this is after 12 months for all the cases, we can see some differences from the three exposures, but this is just on the surface. And after cleaning the specimens, for example, for the geothermal exposure, we can see that there is no leaching on the surface, which is a very common phenomenon for ordinary concretes. And for chlorides, since we have corrosion, usually we observe the inner parts of the material, and here on the outer layer we have some corrosion, some rust on the steel fibers, which is not the case for the inner layers, thus meaning that chlorides did not penetrate deeply inside the matrix. Then I will just propose some comments on the different methods we use to address some properties. In this case, we have the elastic modulus. As you can see, most of the measurements are really close to each other. And also, they confirm the observation from mechanical testing present in literature. This means that as a practitioner, if I want to apply one of the methodologies and I'm not able to decide which one, any of them can be suitable to address the evolution of the performances because they are in good agreement within each other. We have some differences, especially between the two ultrasonic pulses methods, due to the path the waves have to follow inside the specimen. Because of course, while direct waves can pass through the undamaged section, the indirect waves are more affected by the presence of cracks or sealing on the top layer, which is the tensile phase of the section. And this is why we have some faster traveling time for the direct waves compared to the indirect ones. And for the two methods proposed to determine the constitutive law, the constitutive response of the material, there is a clear increase of the properties in the case of inverse analysis if we compare to the direct tensile test. But what we discussed about this was the that tensile test had two different problems, which on one side is the distribution of the cracks. You can see from this picture of the section that cracks are mainly distributed on the bottom of the slab. Thus meaning that if we test it under flexural loadings, it is very effective into acting as a tensile reinforcement. But when all the section is under tensile stresses, we experience failure from the side where we had poor content of fibers. And the other issue related to tensile test is the permanent deflection we had on the specimen, specifically after 9 or 12 months, which then causes to fail not under tensile, but under flexural and tensile stress. And for this reason, we had lower values of stress. And these are some concluding points. I already discussed most of them throughout the presentation. I don't want to bother you more about this, but just to add some comments on the methodology, as I said, for the non-destructive methods, we observed very good agreement within each other, which means they might be interchangeable in case we can do just a few of them. And another possible suggestion for future works is to address longer periods of exposure, even though we know PhD is just 3 years, so might be challenging to follow these longer periods, but might be interesting to see if the properties start degrading after such a long time. And for our material and for the exposures we observed, of course, the self-healing capacity of the material was confirmed, and specifically the nano-additives fostered the healing and the mechanical performance of the material. While for the exposures, we observed some positive, let's say positive contribution from chlorides to seal the cracks due to the binding of chlorides inside the matrix, while for geothermal water, the sealing process was hindered in some cases. And that's all. Thanks for your kind attention.